Welcome to lecture number 31. We are studying probability and statistics, and in this lecture we'll continue studying Bayes rule. We started studying Bayes rules in our last lecture and we solved a couple of examples there. Today we'll solve an example related to medical diagnosis tests. The example is that we are given these two probabilities, this one and this one. Probability that a medical test gives us uh, that the result that the disease is there, given that the disease was actually there. So it produces a result, it detects a disease, the test detects the disease when the disease is already there, when the disease is actually there. It's 0.94. In medical terminologies, we call it true positive. Truly it has detected a positive presence. So the test is true, it's there, and we have the test has detected it too. Therefore, we call it true positive. So so this is a very important term, and ideally true positive should be 100%. It should be equal to 1. If the test is detects, the test should always detect if the disease is there. But no test in this world is 100%. So if the disease is there but the test doesn't detect it, this is this term we call it false negative. So the result is negative and it is falsely negative. Why falsely negative? Because the disease is actually present. So therefore it is negative, but it is falsely negative. Alright, so in these two terms, the probability that the test is positive given the disease is there, and the probability that test is negative given the disease is there. True positive and false negative. They should sum to 1. So we are given in this example, we are giving only the true positive, this probability. So we can find out this false negative easily by subtracting this 0.94 from 1, because we know that true positive and false negative, they sum to 1. So this is what we have computed. So we were given the probability of true positive and we computed the probability of false negative by subtracting this 0.94 from 1. Right. One other thing that we are given in this example is this true negative probability. True negative means that the disease wasn't there and the test detected a negative result. This means it has truly eliminated the absence of disease. So this should also be very high. It should also be exactly 1 or 100%, but practically this is very large for good tests. So this is true negative, true negative. We know that true negative and false positive. False positive means that the disease isn't there, but the test has falsely detected it to be there. So falsely won. Therefore, this is false positive, falsely positive. It wasn't there, but the test detected it to be. So therefore, it is called false positive. So these two probabilities, true negative and false positive, they also sum to 1. Therefore, we can compute the false positive probability of false positive given the probability of true negative. How? By subtracting it from 1. 1 minus 0.98. This is 0.02. So we were given these two probabilities, true positive and true negative, and we computed false negative and false positive. So this probability was also computed given these two probabilities. Which two? True positive and true negative. And we have computed false negative and false positive by subtracting from 1 these two values. 0.94, we subtracted 0.941 minus 0.94, computed false negative. We subtracted 0.98 from 1 and computed false positive. Right, given all these probability values, we are also given that the disease is present in only 4% of population. This means if the disease is present in 4% of population, this is given, this means the disease is not present in 96% of population. So this is what we can compute by subtracting probability of d is equal to 1. D is equal to 1 means the disease is present. So d is equal to 0 would be 1 minus 0.04, this is 0.96. So if it is present in 4%, it is not present in 96% of the population. So given all these probability values, how many? 1, 2, 3, 4, 5 and 6. We can find the unknown. There is only one unknown in this problem, that is that given that the test is positive, what is the probability that disease is actually there? So we know this probability. D is equal to 1 given t is equal to 1 given d is equal to 1 means that the probability that disease is there and the test detects it correctly, we are given this probability. But what we are being asked is the reverse probability. D is equal to 1 given t is equal to 1. Given that the test detects it, what's the probability that disease is actually there? So you can find out the difference between these two terms easily. In this term, we are given that disease is there, and what is the probability that the test detects it positive. Here we are given that test detects it positive. What is the probability that disease is actually there? So this probability is reverse of this probability. So how would you compute that? For that, we know that we have to take help from the famous Bayes rule. We studied Bayes rule in earlier lectures, lecture number 29 and lecture number 30. So Bayes rule suggests that to find out, this Bayes rule is actually used to compute the reverse probability. The reverse probability is computed as this forward probability times d is equal to probability of d is equal to 1 divided by this evidence probability of t is equal to 1. For this term, we have to go back in lecture number 28 and 29 where we studied law of total probability. Law of total probability is that for any event t to be 1, we find out all the dependencies. It is dependent on d is equal to 1 or d is equal to 0. So we have to find out these two joint probabilities, and if we test all the possibilities of this second event d is equal to 1 and d is equal to 0, in this case, if we try all the possibilities of the second event and keep on adding those terms, we call it marginalization. To marginalize t is equal to 1, to marginalize this d variable or this t event, we have to try all possible values of d, and we have to keep on adding these joint probability terms. So here we have only two options for d is equal to 1, d is equal to 0. So we have to add these two joint probability terms to marginalize this d event, and then we'll be left with this t is equal to 1, the probability of t is equal to 1. We know that this joint probability can be written as the conditional probability times this marginal probability, and the same lines. And on the same lines, this term can also be written as like this. So fortunately, we know all these values from the list given on the last slide. T is equal to 1, given d is equal to 1, it's given to be 0.94, d is equal to 1 is 0.04, and these two terms are also given. So we come up with probability of t is equal to 1 equal to 0.0568. So now we are almost done, because we are going to put it probability of t is equal to 1 in this equation number 1, and then we're done, because the terms in the numerator are already available to us in this list. We know this, d is equal to 1, given t is equal to 1, given d is equal to 1, and probability of t is equal to 1. We know these terms. We have to just plug these terms in the numerator of equation number 1, and in the denominator we'll put probability of t is equal to 1 equal to 0.0568. We have just computed, and then we are done. So like this, we put these values, and now we come up with this probability. D is equal to 1, given t is equal to 1 means given that the test produces positive, and what is the probability that the disease was actually there. So this is how we have solved this simple problem using Bayes rule. Right, that's all for this lecture. Thank you.